Everyone, welcome to Groundwater Talk Live. I'm Tom Ballard, the groundwater guy. We had to reschedule our guest that we originally had planned today, so we're going with a little bit different alternate topic that I think should be of interest to folks. We're going to talk about locating new water supply wells in Middle Tennessee by using a combination of FTLA and hydrostratigraphic analysis. For those that don't know, FTLA stands for fracture trace and lineament assessment, where we're really looking uh, at fractures, fracture traces on the ground, and using those to locate water wells. But when we combine that with hydrostratigraphy, then it becomes a really powerful combination to do the best possible job in locating water wells. But before we get going, if you can like, comment, and share, I really appreciate it. It helps us get the word out there. I reply to all comments on the YouTube videos. You can find us on LinkedIn, YouTube, Twitter, and a bunch of different places. But I reply to all the comments out there and really appreciate them all. But even likes and shares really get the word out there and gets us more subscribers. So I appreciate that. All right, so let's move in and talk about this. What I'm going to discuss today is two sites that we looked at that are in Middle Tennessee, and they are located in what we call the Central Basin area. Now, the Central Basin is called the Central Basin because it's a topographic basin, but it is geologically a dome. So you'll see a slight dip away from the center of the dome, but it's fairly flat lying for the most part, but with just a very slight dip, and it becomes a little steeper in different areas. But you do need to take that into account. So there's really two parts of the Central Basin. There's the inner Central Basin and the outer Central Basin. The inner Central Basin has the lower units. These are going to be mainly Ordovician limestones, and then below that you get down into the Cambrian Knox Formation, and above that you have the Devonian Chattanooga Shale, which is kind of a regional aquitard, and above that the limestones of the Highland Rim. So we're really focusing on the Ordovician section that is really what makes up the Central Basin of Tennessee. So let's look at that. This is in the red, the crosshatch there in the middle is the Central Basin area. So like I say, it is actually geologically a dome. And that's kind of what we're going to be looking at. We got a couple different um, locations we're going to look at today. One is kind of on the north, I guess you could say the northeast side, east of Nashville. And the other side is kind of on the southwest side of the Central Basin, basically south of Franklin, Tennessee. Those are some prominent locations there. And those are the two sites we're going to be looking at today. Similar geology, but we're going to kind of look at how we look at the local geology and the well data to really get a good assessment of where to put the water wells. All right, so the stratigraphy of the Central Basin, and I know this is kind of small and hard to read, but the point here is we really have what's in blue here are the units, the limestone units that tends to karstify and form a little bit more of an aquifer. They got aquifer characteristics in most places where they do get the karstification. Now, karst is a huge part of Middle Tennessee, and the degree of karstification, so really the depth is going to be really important as to whether we're going to get a productive water well. So fracture zones are obviously going to be important to start to develop that karstification. So that's really what we look for. But we also need units that are a little bit purer limestones, a little more massive, that tend to readily karstify when they get those fractures. So that's why a combination of hydrostratigraphic analysis, really looking at the geologic characteristics and hydrogeologic characteristics of these units, plus the fracture trace, really is the best methodology to locate water wells in this area. And I would argue, and we've talked about this in some past shows, I would argue that a combination of those two methods is really the best most everywhere. Now, sometimes you get into alluvial environments, and it's strictly the hydrostratigraphy, and fair enough. But generally, when you get into a bedrock environment, it's going to be a combination of the two. So what's important here is we start at the top here with the Cathay's formation, and usually the leapers is going to be in there too. They're usually lumped together. The leapers and Cathay's formations are lumped together. That can karstify, and you can get water wells in there. Generally, it's not going to be a great yielder. That tends to be about 125 to 400 feet thick, depending on where you are. And then we move into the first hydrostratigraphic unit that yields water, and that is the Bigby and Cannon limestones. Those tend to run about 60 to 150 feet thick. They do tend to karstify. As a matter of fact, the famous caves that provide the water for Jack Daniel's Brewery down in Lynchburg are in the Bigby limestone. So that can be a great yielder, and they get a lot of water out of there to produce their whiskey. I don't know if they if all the water for their whiskey comes from their cave, but it certainly has a good flow out of there. I've been and visited that. So below that, you get the Hermitage Formation, which is more of an aquitard. It's a shaly limestone, and that runs about 50 to 100 feet thick. Now, the Hermitage is once again generally considered an aquitard. You can get wells in there in certain circumstances where you get a little bit more limestone rather than the shale. It can karstify, and this holds true of any of these that I have marked in brown here that are generally considered aquitards, but generally it's not a target that we want to look at, because you're just, even if you do get wells there, maybe for domestic use, the yields aren't going to be that great. So, and you'll notice here we have an alternating aquitard and aquifer, aquitard, aquifer, aquitard, aquifer, and then aquitard, and then actually below the Pond Spring Formation, which isn't present everywhere. Usually we consider the Murfreesboro limestone to be the bottom of the Ordovician. You get into the Cambrian Formation, which is the Knox Formation, the upper part of the Knox Formation, and that actually can be a decent producer. There's a paleokarst at the top of the Knox Formation, and that can be a target. However, typically you're looking at drilling wells of 1,000 feet or more, which in some parts of the country is not that unusual. In Tennessee, we usually try to keep 200 to 300 feet is generally what we're looking at. So we don't generally go to the Knox Formation, although people have tried, and it can be hit or miss. But the paleokarst really is a regional aquifer down there, and actually extends into neighboring states. So you do get some regional groundwater flow down there in the Cambrian. But today we're focusing on the Ordovician. So once we get down below the Hermitage Formation, we get into the Carter's limestone, and that the Carter's limestone has some unique features. It runs about 65 to 250 feet thick, depending on where you're at. It does contain some bentonite beds, and probably the most well-known is the upper part of the Carters. It's called the T3, or the Pencil Cave Formation, which is what the old-time drillers called it, just because it's a very thin and tended to erode out and during the drilling, so they called it Pencil Cave because it was so small. But it's a relatively consistent marker bed, and you know when you're in those bentonite formations, they can act as aquitards. So sometimes you got to look at, are those bentonite beds, specifically the T3 bed, are those breached or not? So down below the Carter's limestone, we get the Lebanon limestone, which is more of an aquitard. That tends to run about 115 feet thick. The Ridley limestone below that can be a good producer, and you'll see that we did target that in one of our investigations when we talk about the individual properties. So the Ridley runs about 100 feet thick. That will karstify if it's near the surface, and that's important with karst. Is if you're close to the surface, then you'll get better karstification. Generally below 300 feet or so, you're not going to get those karst conduits developed, and the yields are going to be lower. So below the Ridley, we get the Pierce limestone, which is another shaly limestone, not as good a producer. That runs about 25 feet thick, so it's a fairly thin bed. And below that, we get the Murfreesboro limestone. Generally, it's a fairly thick one, about 425 feet thick. Where it is at the surface or very near the surface, it can be an excellent producer because it's a fairly pure limestone. It karstifies readily, so you get those solution channels that you really need for the water to move through there. And below that and above the Cambrian is a pond spring formation. That is not present everywhere in Middle Tennessee. Generally, I consider the Murfreesboro limestone to be the bottom of the Ordovician sequence in the Central Basin. So there, that is the stratigraphy, and a little wordy here, but the important thing is the rhythmic sequence we're seeing here of aquifers and aquitards. So this is where our hydrostratigraphy comes into play. We want the fractures, but we want to make sure we're in the zone where it's going to karstify and produce the and produce the water we need. All right, so like I said, we have the outer central basin, the inner central basin. Let's look at the hypothetical groundwater flow, and generally the groundwater is going to be flowing left to right here at the top here, and this is the outer central basin. So the upper part of the Ordovician that we talked about. The Big B and Cannon limestones tends to readily karstify, and we actually see this. I've taken some tours of some dams, and Center Hill Dam in Middle Tennessee is a great example of this. They've spent years and years trying to plug these holes in around the dam and the formations where these karst conduits developed, and they've just kind of concluded they just have a leaky dam, and because you put some concrete in here and it just springs up somewhere else. So and that's in the Big Buchanan limestone. So it does readily karstify, which and when it comes to wells, that can be a good thing. Now the thing is it a little too shallow, or are we missing too much of it, and we can't get enough to drill a productive well? So we need to kind of look at that. Below that, we have the Hermitage Formation. Generally not a good well yielder. It's a scaly. The water does not move through it. You don't get much karstification. And then below that, you get the Carter's limestone, and that does karstify. However, that bentonite bed we talked about, particularly the T3 bed or the Pencil Cave Formation, as the drillers call it, is located right up there. That's going to be a fairly thin bed, just a few inches thick, but it's enough to impede the downward flow of water. And so you're going to, unless that is actually breached in places by erosion, then you may see less karst development below that, and it may not be a good target for water wells. But certainly the upper part of the Carters is a good target location for water wells. Now, if we move to the inner central basin, which is the deeper units, we start off, and if you can see on the right here, we're talking about the alternating hydrostratigraphy here again. So you got the Carters or the Ridley, and then below that, the Lebanon or the Pierce, depending on how deep you are. And the Lebanon and Pierce are both shaly limestones or aquitards, so you don't get much karst development. And below that, you get the Ridley or the Murfreesboro limestone. And the Murfreesboro limestone, like I said, where it is near the surface, it can really karstify and produce some pretty good wells. But if you bury that much, then you don't really get, if you're below 200, 300 feet, you're probably not going to see much karst development in the Murfreesboro limestone, so it's probably not going to be a good target for wells, unless you have some pretty good fractures developed in there, but that's going to be more the exception. So generally we try to look at the Murfreesboro as a hydrostratigraphic target if it's within 200, maybe 300 feet of the surface. I'll sometimes take a poke at it if it's within 300 feet, but if it's below that, generally we're probably not going to see any adequate yields. All right, so now now we're talking about we finished talking about the stratigraphy. Let's look at a couple properties, and like I say, one is south of Franklin. That's the one we're going to look at first, and the other is east of Nashville. That's the one we're going to look at second. So we'll start off here in Google Earth, and I will show you. Let me just bring this up here, and I will show you where this first one is located. So this is over in Columbia, and let this kind of come up here. I'm using a topographic base here, but what we got is here we have our property here in yellow. You can see the fracture traces I have mapped out there, basically from different sources. And the way I do this is I'm going to go in and I'm going to look at that when I do the fracture trace or FTLA analysis. I'm going to go in and I'm going to look at different data sources. I'm going to look at satellite photography, aerial photography, digital terrain models, LiDAR. And so I'm going to color code these based on different, you can see purple, you can see blue, you can see red. These are all from different sources. And then we go out and we field check those in the field and mark them out to make sure they're real linears. And then we stake out our well locations. So you can see I've selected four well locations here. So that's kind of what we're looking at here. Based on fracture trace analysis. I always like to go and look at the other water wells in the area. And you can see that relative to our site, I classify these as purple is generally going to be 5 gallons per minute or less. Yellow is generally going to be about 5 to 20 gallons a minute, and then green is going to be 20 gallons a minute or more. And that's generally how I classify these. So if you see purple, it's going to have a yield. You can look on here. The yield is what? Yield of 0 in this case. So 0 to 5 gallons a minute. However, we go over here. Here's 48 gallons a minute, and so that's something I'm interested in. This one is 202 feet deep. The yield here is actually 48 gallons a minute. So this is definitely well within the range of what we're looking for this particular facility, which is going to be a commercial facility, an agricultural commercial facility. And we can see here also, here's a 50 gallon a minute well, and that's 205 feet. So we're starting to see kind of a pattern here of your more productive wells are about in the same range. This well up here is a little bit more of an anomaly. It's 270 feet deep. And actually had 100 gallon a minute yield. However, poor water quality. It had sulfur in it. And sulfur is something you can get in Middle Tennessee that contaminates the water. So it's kind of hard to predict sometimes. We can kind of play with that a little bit, but there's not a 100% guarantee you can avoid sulfur in certain circumstances until you actually drill the well. But we start to look at this. So we're looking at the patterns here, and we see that right around 200 some feet deep is where you're going to run into your best producing water, and these are going to tend to be a little shallower, and so that's kind of what we're looking at is where are we at in the geologic section. So let's move on to our next. Let's look at this here. This is our geology map. So what you can see over here is you have the Big Buchanan. So we're kind of in the upper part of the Ordovician, so your outer central basin here. You have the Big Buchanan Formation here. Directly underlying the property, you have the Hermitage Formation, which we know is generally not a good producer. So we're not going to want to drill a shallow well here. And then deeper down, you have the Carter's Limestone, which those 200 plus foot wells appear to be drilled, the better producers appear to be drilled into the Carter's Limestone from what I can tell from the driller's logs. They're not always really great, but you kind of piece this together and knowing how deep things are and where the different formations lie. So we start to look at that and say, okay, we want to look at fracture traces and then look at how those fracture traces are going to impact karst development in specific hydrostratigraphic units. In this case, the Carter's Formation, generally within a couple hundred feet. So that gets down within our range of where we're going to get good karstification. So we're going to target the Carter's Formation out here. So this is our spreadsheet of all the wells. You can see, once again, the green is the plus 20 gallons a minute. The 5 to 20 is the yellow, and the white is less than 5 gallons a minute. So we can start to see some of the characteristics here. You do have one that's relatively shallow. This may have intersected the top of the Carter's. 270, that's that 100 gallon a minute one that had sulfur in it, so it had poor water quality. And these are all open hole wells, of course. So we start to look at and piece this together. So our recommendations here, and let me look at the recommendations on this particular site, is we talk a little bit about the background here. We reviewed data on 19 existing water wells located within 2 miles of the property to try to get a good handle on that. And so what we're looking at is we did the fracture trace, and now we're doing an explanation of what our 3 hydrostratigraphic units are out there and which ones we want to target. So looking at, in this location, because the Carter's Limestone has generally not been breached below the site because you're in the Hermitage Formation, we want to target the upper Carter's Limestone above the T3 bentonite bed. So that's going to put us in about in that range. That's what we're going to shoot for with the drilling. So in my drilling recommendations, I'm going to give them some depths to look at that. That particular unit is shown to develop the karst conduits. It's shallow enough to get for them to develop. So we expect that to be hit about 60 to 70 feet. So that shallow well we saw that was a good producer was probably in that part of the Carters. You can go deeper in Carters, and that's kind of where we're hitting some of those that deeper stuff. And the 205 footers, that's basically where we're drilling, is into the lower Carters. Now you get down below the pierced and or the Lebanon limestone, and you get the Ridley, which is a little bit deeper. We can expect to encounter the Ridley about 240 to 325 feet. So I recommended that we drill, test the Carters, both above and below the T3 bentonite bed, and then get down to the Ridley, which entail a well about 325 feet or so. Yeah, you'd probably be looking at maybe the deepest well you'd want to put out there would be around 405 feet. Now, I also talked about the Knox Formation. That can be a reliable producer, but you're probably going to hit it at depths of close to 1,000 feet, which is probably not going to be practical out here. Also, the Knox, when you get away from the middle of the central basin, tends to have water quality issues when you encounter it deeper. So high total dissolved solids to the point of making it non-potable. So you kind of want to watch that a little bit. There have been some wells in this area that explored down to the Knox, but not a common development just because it's deep and has questionable water quality. So based on the combination of the hydrostratigraphic analysis and the FTLA analysis, we went and we located 4 locations out here, actually 5. I added another one when I went out in the field just because I picked up on that and added that. We provided GPS coordinates, but the important thing is here is uh, we recommended a boring depth of 70 to 100 feet to intersect the upper Carter's limestone. It may produce acceptable yields. However, we said if you're not getting enough water there, that you're going to want to go explore the lower Carters and then down into the Ridley if you still need more. So this provides some guidance for the driller because they may drill down and they may hit a little bit of water and they say this is as good as it gets, but by providing some guidance for the drillers, they then know that if they don't get adequate water for the needs of the system here, that they can keep drilling and we kind of give them some guidelines to hit. And I can tell you the drillers do appreciate that because a lot of times they're going to go out there and they're just going to drill based on their experience. This gives them some scientific analysis on where to drill and how deep to drill, and then that tells them what they need to do. I find in a lot of cases that's the shallow wells are really a tendency in Middle Tennessee, and they tend to stop drilling too soon. So you drill a 70-foot well, you get 5 gallons a minute, you say good enough, when they could have gone to 200 feet and gotten much better yields. So this is an important consideration, and the drillers do appreciate this kind of guidance because they can keep going to get the yields they need, and hey, it makes them look good too. So if they get that, so. All right, so let's go back to the to Google Earth. Let me switch up my. Um, all right, let's go back to Google Earth, and we're going to go to our other site here. So nope, that's the wrong one. So yeah, there we go. This is going to be up east of Nashville. So um, here we are with our site here. Kind of the same sort of thing, except we are really more in the inner central basins. So you're getting down into the lower units in the Ordovician here. So this is our property. Just kind of zooming in here. We mapped out. I don't have these color coded in this particular case, but we do have these mapped out, and I think kind of the thickness of the lines here is hard to see. Actually, it's what I used on this one for different sources, and then I went out and shifted things around a little bit. But you can see once again we're looking for intersecting fractures here, and those fractures are derived from the usual satellite photography, aerial photography, digital terrain models, lidar when we can get it, and other sources that allow us to look at potential structural trends based on linear features on the ground. And that's what we map out. Then we go out and we check that in the field and confirm that they're there, or whether they're, a phantom feature that just showed up and is not real. And we discard those and shift our well locations. And so we came up with this is a private property. He's looking for a domestic well. So we came up with 4 locations for him. I didn't like well location 4 quite as well. It's just kind of less distinct even when you're out there. So I really gave that a much lower priority here. But let's back out here a little bit and look at some of the characteristics of some of the wells in the area. So we have, once again, the same color scheme you can see here, and maybe it's a little bit better if I turn off the topographic. You can see here, here's our wells within 2 miles of the property. There's a few wells in green here, and they have some common characteristics. So this is a 40 gallon a minute well. The well depth here is 125 feet, yielding 40 gallons a minute. And this one here is actually 110 feet deep, yielding 21 gallons a minute. And some of these other wells, this one is 116 feet deep. This was getting around 5 gallons a minute, so probably adequate for domestic water supply. This one over here, 114 feet, 15 gallons a minute. So once again, adequate for domestic water supply. So I think we're seeing some trends here. They're about 100 some feet deep here, the better wells. Now you'll also notice I have some of these. There's some really poor wells here, but there are a number of wells here where the water is bad. It's listed as bad, and I'm assuming that's going to be sulfur. So it is scattered around here. It is a problem out here. So you got to watch that a little bit. But based on these trends, we can see we're hitting a specific depth. So let's go back and look then at our geology. Just change that up there. Yeah, so here we go. This is the geology of the property. And you can see we're actually at the property itself. We're a little bit farther down in the section than our last property. But what we're looking at here is we're down in the lower Carter's Formation at the very bottom of the Carter's formation or Carter's Limestone. And below that, you get the Lebanon limestone, which, as we talked about, is not a good yielder. It's more of an aquitard, so you're not going to get good wells there. But below that, we get the Ridley Formation that really is not showing up on the surface geologic map because it's relatively flat out here. But the Ridley Formation does show up below the Lebanon limestone. And coincidentally enough, as you look at the thicknesses of the individual formations out there, that 115 feet or so that we're seeing from the better producing wells on the wells database coincides with the upper part of the Ridley limestone, which does indicate that it's shallow enough that it karstifies pretty well, as is the tendency of the Ridley. And the Ridley in this area and actually into the Murfreesboro area and a lot of the areas around there is known as a cave former. So there are some significant caves. So we know when it's close to the surface, it does karstify, and that is excellent for us for looking for productive water wells. All right, so let's look at the spreadsheet here. And like I said, you can see we got 2 green wells. We have a number of yellow wells here. Some of the yellow wells are bad quality water, and those tend to be down deeper. Now, these deeper wells here, 350, 290, 410, those look to me like they are down in the Murfreesboro limestone, which would then be below the Ridley, below the Pierce, and into the Murfreesboro limestone. It's going to be deep enough. You're not going to get good karstification down there. And you're seeing in some locations, you're seeing poor quality water. So that tells me the Murfreesboro limestone is probably not a good target in this area. And we want to stick with the upper part of the Ridley Formation, or Ridley limestone. So let me, whoops, sorry about that. Let me go to my recommendations here. And once again, we looked at, we did an analysis of the wells and we did our fracture trace analysis, but now we're looking at how deep we need to drill out here. So we talk about 2 hydrostratigraphic units. The legitimate hydrostratigraphic units in the area. I also discussed the Murfreesboro limestone here and why it may be a hydrostratigraphic unit, but it's probably not a target for us here. So the lower Carter's limestone below the T3 bed here, I don't think we have enough Carter's line. We may only have 40 feet, 20 feet present there. That's just not enough on the surface to really get a decent well. So I believe that you're probably not going to get any significant yields from the Carters here because there's just not enough of it left there. So you're going to have to drill down through the Lebanon limestone and get into the Ridley limestone, which appears, based on the well data in the area, to be a decent producer. So we're looking at you're probably going to be the bottom is going to be around maybe 325 feet. I think that the well is going to be 185 to 205 feet, kind of coinciding with what we saw in the well database. So we put together 4 locations here, and once again, here's our well construction recommendations that we're saying you're probably going to want to drill a well 185 to 205 feet. Now, the bottom of the Ridley in this area tends to get a little shaly, so you want to avoid that. You want to stay in probably in the upper 3/4 of the Ridley formation is really what we're looking at there, and we discussed that. So that's an important consideration here. So the Ridley Formation is probably our main hydrostratigraphic target here. We combine that with the fractures out there, and we should be able to get some good karstification developed in those locations, and productive water wells, at least productive enough for domestic water well situations. So that is, in a nutshell, our analysis of those 2 sites. Hopefully you follow the reasoning that we went through, and how you can combine fracture trace and lineament assessment, or FTLA, and hydrostratigraphic analysis to come up with a good study for locating a water well. Now, I will say that we tend to pick, we may be looking for 1 location, but I tend to come up with at least 3 locations, depending on the size of the property, and then prioritize those, because sometimes, in spite of your best efforts, the geology just doesn't work out, and so you may need to go to an alternate location. So we always provide 1 or 2 alternate locations that if you need to drill another hole, then you can go over there, and generally that's going to be what you need. If the first one didn't quite work out the way you wanted, you're going to want to have an alternate. So I always do that as well. So that's important. But then we prioritize them and say, this is probably going to be your best bet, and second bet, and third bet, and go from there. So there, in a nutshell, is it. And thank you. If you got any questions, please leave me comments, and I'm happy to answer them. Hopefully this has been instructive. This is specifically relevant to Middle Tennessee, but the same principles apply to any bedrock wells wherever you're at. So hopefully you can find a way to apply that. Thank you very much, and we will see you next Thursday.